This is lesson 4 in the GCSE Forces and Balance topic entitled Gravitational Force and Weight. By the end of the lesson you should be able to recall that all masses create a gravitational field and recall the shape of the field close to and far away from the Earth. Recall that weight is the force of gravity that acts on a mass, and recall how to calculate weight using the formula W equals mg. This little section does need to go into your notes, so can you put the title Gravitational Force? The first point to be made is that every mass produces a gravitational field surrounding it. The bigger the mass, the stronger the gravitational field. So although us as individuals have a gravitational field associated with us, that gravitational field is very small because our mass is very small. Whereas we do experience the Earth's gravitational field because the Earth has a relatively large mass. Also, the closer you are to the mass, the stronger the gravitational field. So as you move away from the Earth, the gravitational field gets weaker. And to illustrate that, we can look at a diagram showing the Earth from a large distance. These lines represent gravitational field lines or lines of force. They are the direction in which a mass would move if you placed it in that position in space. Now, if you notice over large distances, these gravitational field lines get further and further apart, and that tells us that the gravitational field gets weaker as we move away. So the further the field lines are apart, the weaker the gravitational field. Now at the surface or near the surface of the Earth, the gravitational field remains pretty much constant. The field lines hardly diverge at all. So we can assume really that the field lines are parallel and that gravitational field strength remains constant at or near the surface of the Earth. Weight is the force acting on a mass in a gravitational field. People often get confused about the difference between mass and weight. Mass, if you like, is a measure of how much stuff there is in something and doesn't change wherever you are in the universe, whereas the weight is the force of gravity acting on that mass. So if the force of gravity changes, the weight of a body changes. So on the moon you would weigh less because the force of gravity on the moon is less. Your mass would be the same. Please take time to complete that note. This slide here is going to take you how we can actually perform calculations to work out a person's weight, and again it needs to be in your notes. So remember at the start of the topic we looked at contact and non-contact forms. I remind you that gravitational force or weight is an example of a non-contact force. Weight, as we've mentioned earlier, is the force that acts on a mass that is situated in a gravitational field. Now this is the crux of it, and it's a formula that you will need to learn. So if you've got a system of highlighting those formulae you need to learn, this one needs to be highlighted. The weight of a body can be calculated by multiplying its mass, m in kilograms, by something called the gravitational field strength in newtons per kilograms. Now this figure is unique to a planet. So on the Earth, for example, the gravitational field strength is 9.81 newtons per kilogram. So that simply means if you hang up a kilogram mass on a force meter, it would read 9.81 newtons, approximately 10 newtons. So it's a very, very simple formula to use. Just make sure that you're using the correct value of G here, which will be given to you in a question, and that the mass is in kilograms and not grams. So, little example then. If a certain teacher has a mass of 70 kilograms, this must have been written a long time ago, what is his or her weight on the Earth? So, just pause the video, do your little calculation, come back to me in a moment. Okay, if you perform that calculation, then you should have found that W, weight, equals m times g, 70 times 9.81, and that gives you 688 newtons to 3 significant figures. So very, very easy to work out. Okay, series of questions then, and a little activity if you want to do this. Again, the information needs to be in your notes so you've got a record of some calculations that you performed. I'd like you to firstly draw up the table shown in blue here, And then I know some people are sensitive about putting information about their weights down, etc. So you can use objects instead of people if you want to just identify what that is. Get a set of bathroom scales, mass it in kilograms, record it in kilograms, not in stones, pounds, ounces, or whatever, in kilograms, and then calculate its weight using W equals mg, and can use G equals 9.81. So that's a little activity that you can do at home. Then there are 3 more questions which you can pause the video now and have a go at. Okay, question 1 then is down to you. Question 2, you should have had a solution of 2,943 newtons. Again, check it, approximately 10 times bigger than the mass in kilograms. Skydiver, well, we haven't done terminal velocity yet, that's coming up shortly. But if you calculate his weight and he's reached terminal velocity, there is 0 resultant force. So the drag force will be equal to his weight. So the weight is 589, so the drag force upwards would be 589. 80 kilogram astronaut on Earth would weigh 785 newtons. On Jupiter, however, because the gravitational field strength is 2.5 times that of the Earth approximately, then they'd weigh 2.5 times more, 2080 newtons. And in deep space, the answer would be 0 because there is no significant gravity in deep space. G is approximately 0, so you would be weightless. Okay, to summarise then, you should recall that the Earth's gravitational field is what we call radial, those lines coming out from the centre. But for distances close to the surface of the Earth, the field is uniform. Its strength doesn't change. You should recall that the weight of an object is the force of gravity acting on that mass, and be able to use the formula W equals mg, where G is the gravitational field strength and is about 9.8, 9.81 newtons per kilogram near the Earth's surface. That's it for now. Watch out for the next video on lesson 5.